like that?
Well, I'm just gonna have, my mic is on.
No.
Okay. Just 1 minute here. Let me get you guys marked as being here. Glad to see all of you. My computer wonked out on me and there it goes again. So we've got Celeste, Lyle, Stephanie, Sean. Stephanie, Sean, and Sherilyn and Safra. So let me get this logged into the classroom here. 98962. Okay, everybody. Done echoing? Almost. Okay, good morning. Nice to see all of you. I hope you had a really good weekend. Kind of a nice rainy day Sunday, quiet. And I have you marked for being on time, and I'm really pleased to say that I got to mark a number of you for having all of your assignments in on time, none of which I've graded yet. And so I just want to work here, and I think it doesn't want to work. So give me a moment, and I want to get you marked for the being on time to class as well. And I was here, but my computer did a blackout on me, so I had to reboot all of that. Okay, just getting these marked. Okay. I think I have got it all set. All right, everyone, I'm glad you're here. So this last week, we worked with the one sample t-tests, and from my perspective, there were just problems with two of them that were really drove you crazy, I'm sure, and really bothered me because it might have undermined your confidence in what you're doing, which is the worst thing that I would ever want to do. So I will tell you that with some reassurance that this week, the concepts are like just the same. And there's only 3 practice this week and they're, so if you lost a little confidence last week, you'll be able to regain it this week because we're doing the same thing. There's just a minor change that we're working with this week. So any questions right now before we get started with our paired samples t-test? Anything? Can I hear some voices? I'm feeling really lonely in this room here. Virgie is too. Nobody's talking to us. I don't know how Virgie's feeling. I'm joking. Can I hear some voices? Lyle, good morning.
Dr. Russ, good morning. And your student there, Virgie, is it Virgie?
Yeah.
Yeah, good morning, Virgie.
Good morning. We miss all of you here, but we're glad you're online. Sean, good morning.
Good morning, Dr. Russ.
Celeste, good morning. Celestin or Celeste, whichever you prefer.
Good morning.
Safra, I'm happy to see you. Good morning. Can I hear your voice? Safra, you're muted. I think you're maybe speaking, engaging with someone else. Colin, nice to see you.
Good morning.
Stephanie.
Oh, yeah, it's a good been everyone.
Hey, everyone. Sherilyn. Sherilyn, nice to see you. I hope you are able to pop in here. Sometimes we step away for a moment. Okay, let's get started. Where's my piece of cardboard? So, we'll start with a very quick review of our nice calculations because we're going to do those again today. And I just want to give you some guidance. I met with Melissa yesterday and she had a good question. So I wanted to just point out something to you. So we have this process that we go through for figuring out our comparison distribution. And it's just these 5 steps, right? First, we figure out the sum of squares, which is just equal. You can write these formulas down. It'll be helpful to you, which is just equal to the score minus the sample mean squared. That's it. It's the same thing we did from chapter 2. And so then step 2, we figure out what we're calling the E-var. And for those of you who are basing your work on the book of course refers to this, and most textbooks do, as S squared. E-var I like a little better. And all we do is we take the sum of squares, and whenever we see this little e, that means we're dividing by degrees of freedom because we're estimating. So that little e means estimate. And that, in our case, means divide by degrees of freedom. And so this is the only place we're estimating. From now on, we just do what we're already familiar with. We calculate VARM, the variance for the distribution of means, which your book and other places will refer to as the variance, S squared, for the distribution of means. And that's simply equal to E-var divided by N. And we're just doing that so that we're not comparing samples of 16 with a distribution for scores of individuals. So we're just making sure we're comparing, say, a bucket of apples with other buckets of apples. Then we're able to easily calculate I don't need that 2 there, the standard deviation for the distribution of means. And it's just this S now, because it is estimated, but it's estimated based on this. So we're not doing anything different here. We already did the estimating, but we use this S so that we're clear in how we got to this number. And all that is the square root of varm. And from here, we can figure out our t-score, which is just the sample mean minus mu divided by spread, which in this case is S. So what I wanted to point out to you is that, let's say you're given a problem and they give you varm. That's what they give you to start with, and they say, find the t-score. So when you get this, there's no need to go back. If you're starting with varm, then you don't do these. You just continue on to number 4 and to number 5. If you're given SS, sum of squares, then you do all of these steps. If the number you're given is E bar, the estimated variance right here, then you start with number 2, but you don't need to go back and get the sum of squares. So you never need to go back. You just always work these steps in sequence to get your t-score. So any questions or comments about this little piece of information that I gave you? Okay, well, we're gonna just start our new content then by starting with a problem right off the bat. So I'll open up my slides in a moment here. So what we're beginning, you'll notice your book put these in one chapter, even though they might seem really different to you. So what we're going to start with, and I'm just going to use an example here. Let's say that I'm interested in whether people have more assignments on time once I start giving points for that than beforehand. And so I count the number of assignments before, like this. And so this is, we're calculating on-time assignments. And so I calculate for the start of the semester before we started doing rewards. And so let's say I have student 1, student 2, student 3, ... let's say down to student 10. And I know that each of these students had a certain number of assignments that were on time before. And so let's say the student 1 had, 15, and this had 12, and this one had 4, and 3, and 16, and 11, and 10, whatever the numbers were. And so now that I've started giving rewards, let's say I count again. Let's say there are the exact same number of assignments. And now student 1 has 18, student 2 also has 18, student 3 has 15, next student has 12, we have 15, 18, 20. So let's say we have something like this. So this looks really different from what we've been working with, doesn't it? Because now we have 2 scores for each individual. But what we're going to do in this unit is what we're really interested in is change. That's what we're interested in. Did the number of on-time assignments change from before to after? And so what we'll be doing is we'll be using what we'll call a difference score. And all the difference score is taking the after scores and subtracting the before scores. Or we could call these scores X1, the scores we gathered first. We could call these scores X2, the scores we gathered second. And we could call this X diff, the difference scores. And we could say X diff equals X2 minus x1. And so these mean exactly the same thing. And so we're going to calculate these. We're going to take, 18 minus 15 equals 3. 18 minus 12 equals 6. 15 minus 4 equals 11. 12 minus 3, 9. 15 minus 16 equals, did I do that right? Equals -1. 18 minus 11 equals 7. And 20 minus 10 equals 10. So once we've calculated these difference scores, we cross off all of this stuff. We're not going to use these anymore. We're done. What we're going to use for our sample mean are these scores. So all the rest of this is irrelevant. So using these difference scores, we're going to calculate the mean. So we're going to get mean difference. And that would just be the sum of all the x difference scores divided by n. And then we'll go on with our regular work that we've done all along. We'll calculate sum of squares in exactly the same way. Equals the sum of x, each x difference score minus mean difference squared. We'll calculate E var just as we did before. E var equals SS divided by degrees of freedom. We'll calculate varm just as we did before. Equals E var over n. We'll calculate, where are we going? Sm as we did before equals the square root of varm. And we'll calculate T as we did before. Equals welcome, whoever's got that sweet baby. Oh, is that Shannon maybe? Equals m diff minus mu divided by Sm. So you'll see, all of this is exactly the same. The only thing that's different is that we're using these difference scores to run the test. So that's it. So if you were comfortable with that one sample t-test, you'll be very comfortable with this because we're not adding hardly anything at all. So with this really simple explanation, just a description of what we're doing, did any questions come up for you or things that you're like, okay, I'm not sure about this yet? Anything like that?
I have a question.
Okay,
So for that x2 minus x1, will it always be like that?
yes,
Okay, so you subtract the
after minus before.
Okay.
And the reason we do that is if you're, let's say you're predicting an increase, you want the scores to increase like I did in this example, then if we take after minus before, the difference will be a positive number. On the other hand, if I was predicting a decrease, let's say a decrease in late assignments, and then, so we had, let's say, before we had 6 late assignments. Let me write this up over here. Before, let's say 6, after we had a decrease and we had only 3, if we take after minus before, let's see, x2, x1. If we take x2 minus x1, we get a negative number. -3. And so then we'll have the direction be proper for the prediction. Okay? All right, so let's go on to some slides and look at what we're actually doing here in a little bit more detail. Oh, I wondered if you had one more question. What do you think degrees of freedom is in this? If we have 10 students and each student is giving us 2 data points, a before score and an after score, and we're using newsfeed data points to create a column of data. What do you think degrees of freedom would be? Any guesses? It's still n-1, but what should we use for n? I'm kind of trying to trick you. It's not as hard as I'm making it sound.
Would n still be 10 minus 1 would be 9?
Yes, yes, it would be. So very good. So we have 10 participants. We're just having these 10 scores, right? That's all we're using. And so it's still 9. So, yep, degrees of freedom is 9 in this case, even though we have 2 scores per participant.
Dr. Russ,
Yes,
could you show the bottom portion of your graphing of the difference? Where the columns are, EVAR, VARM, SM, and T. Thank you.
that's what you were looking for?
Yeah, I'm writing it down. That's why I'm asking.
Good, good, good. Yeah, write it down lots of times. The more you write it down, the easier it is to remember, especially if you write it by hand. You know, typing it in a computer doesn't promote memory in the same way, according to psychological data. Studying this. All right, well, I'm going to get the slides open. I'll do it over on this screen so you can finish writing.
On the T, is that MDiff minus the mu?
On the key.
T, the
On
very,
Yes, the mean difference, and eventually we'll just write it as M, but just so you know, for now, this is what we're dealing with, the mean difference scores. You don't, it's not like a law that you have to write it that way, but it'll help us to remember what we're doing as we get started here.
so it's the mean difference minus the mu.
Minus mu, yeah.
Okay.
We haven't yet talked about what mu is, so we're going to come back to our screen here in a little bit and look at this. So is everyone done with the whiteboard for now? Yeah? All right, let's, I see a chat here. Okay. Okay, so let's look at this. Oh, I wrote dependent samples. You probably noticed that this is a way of calling this test, but I much prefer to call it paired samples, which is an acceptable alternative name and very common. And the reason is because we use the dependent variable and I don't want any confusion in there. So, however, there are lots of names for this test. Look at all these. It's called, excuse me, dependent samples t-test, matched pairs t-test, paired samples t-test, the one I like, repeated measures, because you can see that we're getting the measure twice, we're repeating the measure, or the t-test for dependent means, your book uses that a lot, or the t-test for related samples. But the big essential take home on this is that you have to have 2 data points that are related in some way. So the data points have to be directly related. Point 1 has to correspond in some way with like x2. And so there are a few ways we can do it. So something like this, matched pairs. So matched pairs would be like, we have say I have an example here of relationship satisfaction, wives and husbands. So let's say I've gone to a big program to help husbands and wives appreciate each other more. And I want to know, did this program impact husbands and wives? You know, what, is there any difference in the way husbands and wives were impacted? And so, you know, maybe it's working better for husbands and less well for wives. And so that's what I want to know. So then I would not want to just compare husbands in general with wives. I want to compare like this husband with his own wife, this wife with her own husband. And so those are matched pairs. I'll give you another example I don't think I have in here. Let's say you're doing something really kind of complicated, like you have a new reading program and you want to implement it in 2 different classrooms because that's how reading is taught. Like you can't do it differently. And so what you decide to do is to match each student, each 3rd grader in classroom A with a similar 3rd grader in classroom B. So you match them, let's say, on their general reading level before the program started, and then they're matched. That's another example of how you might match pairs. Repeated measures, that's what we just did. That's the one with before and after scores. Sometimes these can be complicated and have lots of scores, you know, be time 1, time 2, time 3. Comparing scores from individuals at 2 different points in time. That's what we're working with in a t-test. And so an example, we're studying the effect of an intervention designed to help children with dyslexia learn to read. And we want to compare these children's scores after the intervention with their scores before the intervention. So that's what we just did. And then another example are natural pairs, pairs of individuals that are related naturally. This might also fit this first example, but I did a more natural relationship by saying, we're studying the trait of extroversion, and we want to compare one member of a twin set with their corresponding identical twin. So twin A and twin B. Or maybe we're doing something to improve, we have an intervention, and we want to improve the relationship between mothers and daughters. And we're looking at the DV as relationship satisfaction, you know, something like how good are they feeling about each other? And in this case, we want to know, is it impacting mothers and daughters the same, or is there a difference in the way they're responding to this intervention? And so then we might want to make sure that we match each mother with their own daughter. We don't want to have, like, you know, George's mom matched with Heather, you know, we want to get these matched up. So this is what we're doing in these paired samples t-tests. Any questions about this? Okay, we're going to go through some examples, but before we do, I want to invite you to take a look at your first practice, which is just identifying which so we'll go in through assignments and content. We'll go into Unit C t-tests. And now you can see we're on paired samples t-test. It's red. It's due Monday. So you'll get your points if everything is in before Monday. And we'll come to the practice quizzes. First, I'll start with essential concepts because you can see here that things are laid out for you. So all of the work here that we're doing in class, like all those formulas that you just wrote down, they're all right here for you too, okay? So everything is kind of laid out for you. But as we begin here, you'll see that the first practice quiz and there are only three, you'll be very happy to see, I'm sure, is what test? And so there are a couple things to remember. So let's jump on the whiteboard and not the whiteboard. There we go. So just remember a couple things here, and that is that we have three tests that we have worked with so far. We've worked with Z. And let me enlarge this a little. We've worked with Z, and that is comparing a sample mean with population in which we know mu, unknown sigma. We looked at the one sample t-test. And that is a sample mean M compared with known. Whoops, look what I just did. I just made a mistake. Ah, boy. What should I have written here instead of unknown sigma for a z-test? Do we know sigma in a z-test? Yes, a known sigma. And sorry about that. Correct that in your notes, people. Here in the t-test, we have a known mu and an unknown sigma. And in our paired samples t-test, we're comparing different scores. So we're comparing sample mean difference scores with a population and I haven't told you this yet, with no difference. And you'll find out that we know mu, and I'll tell you about that. And we will calculate or estimate sigma. So I don't think I'll go through this in class as we have done in the past, but I wanted you to see that that's what you're doing in the first test. And I want to caution you, because I'll give you a few minutes in case you want to make your first attempt right now, but I'll caution you about something. You haven't yet met the next test we're going to do, which is called independent samples. And in that test, you'll see that we're still going to have two data points. Like we might have data, still two sets of data, but the individuals aren't paired in any way. So we might have people randomly assigned to condition A, have the intervention. Condition B, not have the intervention, but the people aren't connected. People in each connection, people in each condition are unrelated in any way. They're independent. Are unrelated. And there might not even be the same number of people in each group. Whereas in a paired samples t-test, there's always going to be two scores that are related to each other. So an equal number of, say, before and after or mothers and daughters, but they're always going to be equal. But the independent samples is like this. So if you see in a question that people were randomly assigned and they don't seem to be related, well, that's not going to be any of these tests. So you'll have to click none of those tests apply. So be a little careful when you do this. So take a few minutes and go ahead and take your first little practice. And then we'll come back and work on our first example. Send me a note when you're done, please, so I can time this out a little bit. All right, thanks, Virgie. How are you doing, everyone? I want to move forward if you're getting done here. Okay, I'm Sherilyn, how are you doing? Are you here with us? It's always the challenge of trying to, it's like asking people to read something big in class. People have different speeds of approaching it, and then it's hard to get people back on timing.
Dr. Russ,
Yes, Lyle?
we're looking at practice test 7B1, right?
Yes,
Okay, I'm just double checking.
okay. And I think we're going to move forward now and go into our example. So I hope that this is good timing. Sean, are you okay? Ready to go?
Yes, I am, Dr. Russ.
Thank you. All right, so let's move on with our example. So I want to just answer a general question first. You might be asking, what are we comparing these people to? So what we are comparing our sample to is people who had, so let's say let me give you the example first, and then I'm going to come back and answer that question. I think it'll be easier with an example in front of us. So our example today is going to be bullying. So here's the scenario. A school counselor found that when popular school leaders, like kids who are really respected in school, if you can get those kids, those really respected kids, to stand up and defend victims of bullying, the incidence of bullying to these victims decreases. This is an actual initiative that someone told me. She had a child with a disability with like a form of autism, mild form like Asperger's. And her son was picked on a lot in middle school. And that's the intervention they did. They got together they identified who is the leader of the group that's picking on. And they brought that kid in, or maybe a couple, and said, you guys have so much power. You guys are the leaders. People respect you. People do what you do. They did that kind of a talk to them. And it actually helped this child, prevented the whole bullying situation, improved. So that's what this initiative is. So let's say that happened with this one child, it worked. And this counselor says, maybe this would be a good initiative. What if we start a little program? We call it Leaders Lead. We do it in 4 schools. Let's see if it's effective. Maybe it's worth pursuing. So the question is, does bullying decrease significantly after popular school leaders are persuaded to defend the victims in these 4 schools? So we're going to use significance level of alpha 0.05. And so you can see what we've counted are the bullying incidents. I put in 4 I don't think these are the names of the high schools, but I thought I'd make it local. So let's say that happened here. And they counted these bullying incidents, and we want to know, is this a significant difference? And so this is where we'll talk about what the comparison distribution is. So for population 1, we're looking at schools in which the intervention took place. Okay. Schools are the unit of analysis. You could see that from the way the question was asked. So does it decrease bullying, the number of incidents in schools? So schools were the intervention. Now look at what we're comparing it to. Schools with no intervention, or we might say no change. And so here is where I'll just do it right on this slide. So what does this population look like? Well, if they had no change to before from after, then the mean would be 0, right? 0, no change. Maybe some schools had a few more incidents, some schools had a few less incidents, but overall there's no change. And so this is what we're comparing it to. We're comparing it to a distribution that has a mean of 0, always. The population 2 will always have mu equals 0. We're going to estimate the spread, and it's a t-distribution that will be normal. So the dependent variable was bullying. I think I should write bullying incidents. That would be a little more clear, indicating what we're counting. Otherwise, we might say bullying. What are we counting? How rough it is? We're counting the number of incidents. I stated that we have one-tailed low based on this word decrease. So we're looking for a negative number. We're looking for different scores that are lower than 0. So writing the hypotheses is a little bit different here. First, I wrote it out in words. This is similar to how you might write your conclusion, because your conclusion should be in nice, understandable words. Bullying levels after the intervention were lower than before the intervention. That's what we're hypothesizing, right? But that's how you would write your conclusion. And if we're stating it in terms of statistics, what we're really comparing is the mean difference from before to after the intervention. So we're saying the mean difference scores will be less than 0. So we could write our hypothesis that way. We could write mu, and we could write, say, diff, or we could write mu1, and we could write it as less than 0. Or since mu2 is 0, we could write mu1 is less than mu2. So those ways would be appropriate for writing it in shorthand. If it's clear to you, you can just write it out in more understandable words. So the null hypothesis, I just wrote the same thing, adding this word not, like we usually do. Bullying levels after the intervention were not lower than before the intervention. And we could write it this way, mu1. So the mean difference scores for population 1, these intervention schools, were equal to mu2, the schools with no intervention change. Or we could write mu1 equals 0. You can write it out either way. This way is like the shorthand way of doing it. And now let's move on and do the next step. So we're going to be comparing our difference scores. And let's go ahead and do all the math right here. So the first thing we're going to do is figure out the difference scores. And so let's write our x's in here. So this, I didn't leave quite enough room, that's x1, this is x2, and we're going to calculate now x difference. Okay, and we're going to do that by taking x2, the after scores, and subtracting x1, the before scores. So 22 minus 35 is negative 13. See if I can get my pen functions to show up here. All right, I'm going to just escape down into the smaller screen and kind of write this over because I want to be able to, I hope you can see that as well. I want to be able to change the color of my ink here for one thing. Okay, so what we're going to do is we're going to calculate x difference, which is x2 minus x1. And writing it out, that would be 22 minus 35 equals negative 13. 5 minus 22 equals negative 17. 10 minus 17 equals negative 7. 29 minus 28 equals 1. And so now we're done with all this. And these are the scores we're going to work with. Now we proceed as normal. So we're going to take out the normal information that we need to get. So let's write all that stuff down. We know what it is by now. We know we need N, we need degrees of freedom, we're going to need mu, we're going to need M. In this case, it's going to be M diff. We're going to need sum of squares. We're going to need E there, varm, and SM. So in this case, what do we get for N?
Four.
N is 4. I think I'm getting a little small here. I'm going to just erase and spread this out just a little bit more. Make 2 columns. I think I'll just leave it alone until I get everything ready here. I'm just going to leave it and rewrite all that when we get to it, just to make sure I have enough vertical space here. So what's degrees of freedom? And let's see a few people in chat. What are degrees of freedom going to be? Yep, Virgie. 3. It's 3. Mu, what is mu going to be? Mu is always the same. We're comparing it to a distribution where there's no change, where there's 0 change. So what is mu? Anyone? Just say it.
0.
It's 0. Always 0. So you can just remember that mu is always going to be 0. Our m diff. Well, all we have to do is sum the column of the x diff and divide by n. We're not estimating anything. We don't divide by degrees of freedom to calculate mean. And when we do that, we find out that the mean is -9. And so we'll go ahead and figure out our sum of squares, which we know is the same. It is the sum of each score. Each different score is what we're working with now, right? We're working with this x diff column. But it's no big deal. Minus m diff, same as m squared. So let's go ahead and do that. I usually write these out, as you know. So our deviations are going to be, so I'm going to take the difference score, -13, and subtract m diff, which is -9, same as adding 9. And we get -4. Here is -17 minus -9, which gives us -8. Here we have -7 minus -9. Which equals 2. And finally, 1 minus -9, which equals 10. So those are our deviations. We know well enough now that we have to square all of these. So we'll put our deviations squared. So -4 squared equals 16. -8 squared equals 64. 2 squared equals 4. 10 squared equals 100. And now we're ready to get our sum of squares. All we do is add all those up. And if we add all those up, we get 184. So now we're ready to do the same things we did in our one sample t-test. What should we do next? We know sum of squares. Nothing here is changing from what we've done before. So what's our next step after SS? You can look on the notes you took at the start of class if you wish to.
You get the EVAR.
We're going to get EVAR. How should we get EVAR?
Sum of squares divided by DF.
EVAR equals SS over DF. And if we do that, we get 61.33 repeating. What's next? Anyone? How about if I call on someone? See who's here. I don't know. Colin, what's next? Colin. Not here. Alexandra, do you know what's next?
Would it be varm?
Yeah, it would be VARM. How do we get that, Alexandra? Do you know the formula?
No, sorry.
All right, who can help her out?
Dr. Russ.
EVAR divided by N.
Very good. EVAR over N. And this just makes sure that we're comparing samples of, in this case, 4 with a distribution representing sample sizes of 4. And next we can go ahead and calculate our standard deviation for the distribution of means, which is going to be the square root of varm. And finally, and then we're going to calculate our our t-score, excuse me. So we have everything laid out here. The numbers I went ahead and did in Excel, so I wouldn't be doing calculations here where in class, which is always kind of stressful. And I took the square root of varm and I got 3.92. That's a rounded number. The actual calculations, I use the full numbers. And then we know that T is just M. In this case, it's MDiff minus mu and divided by SM. What do we know about this mu? It's always going to be what?
0.
It's always going to be 0. So in actuality, we wouldn't even have to do this, would we? We could just do MDiff divided by SM, and we'd be set. Okay. And I did this math too. It equaled negative 2.30. That's rounded to the 2 decimal places. So let's do the rest of the steps here then. So our comparison distribution, always mu will be 0. Our shape, T distribution, normal. And our spread, SM, we already calculated, and we determined that it was, I should write 4 decimal places. Let me get 4 decimal places, 3.9158. 3.9158. This is our distribution. Handily, it already has the 0 in the middle, which is true. Our comparison distribution has no change. Our cutoff point, we look up the same way. We're going to use alpha 0.05 as stated. DF equals 3. Let's go ahead and get out our calculator. You guys hopefully you have the link to this bookmarked. And so p-value for alpha, same thing, 0.05. Degrees of freedom, 3. And let's calculate. What do we need for a one-tailed? So what should we put down for our cutoff point in this test that we're doing about decreases in bullying? One-tailed low. What's our cutoff? Put it in the chat, please. What cutoff point should we use for our one-tailed low based on what you see on the screen here that I just, Cheryl, thank you, Sean, yes. Minus 2.35, you guys all got that right away. Minus 2.35, we'll cut off right here. Our shaded region will be this area in the tail. Our fail region will be all of this. Any score that falls in there will fail to reject. Our sample t-score we already calculated, and we got minus 2.30. So let's write these in here. We'll write t and then that little alpha equals minus 2.35. And then we have to put our sample score to this side of it. And t equals minus 2.30. And so what does our decision have to be? Our sample score is, everyone type in whether we're going to reject or fail to reject with our sample score. How can I distinguish it? Right here. I'll make it into a little I don't know. That's how I'll distinguish it. Okay, Sherilyn says that we failed to reject. Who agrees with Sherilyn? Give me a thumbs up. Yeah, okay. And Virgie agrees, and I agree. So we're going to fail to reject HO, and let's write up the conclusion. Evidence from this study suggests that bullying incidents do not decrease following intervention. We do the T, our degrees of freedom, typically in subtext, would be 3 equals minus 2.30, and we have to say NS. Now, I have a question for you. So this is all the same as what you've done. If I was this counselor, I'd be really disappointed. And if I went back and looked at the data, do you notice anything different about any of the schools? In terms of the patterns? Because if you were, you'd be disappointed and you'd want to know. It looks like Chinle High, they really decreased. Window Rock High, they really decreased a lot. Juba City High decreased. What happened in Shiprock?
Increased by 1.
It's an increase. So if I were in this position, I'd look at these data and I'd say, you know, I wonder how well it was implemented at Shiprock. Maybe it wasn't implemented the same way I was thinking, and maybe I should find out what happened there, you know. And I might investigate and not give up on my idea if I was doing this research. But you have to find out about these things, because then you have to tweak your plan. Maybe your plan isn't quite as good. So that's a quick example, and that's what we have here. Questions on that example? No? Pretty easy, once you know one samples. All right, let's go on in this example. Have you guys ever heard of Rumspringa? It's real. Okay, so maybe you've heard of Amish communities. Sorry, I changed my dependent variable, so let me change it here too. This is a true thing that happens. So people in Amish communities, they're all around the country. We used to have some where I lived in Wisconsin. You'd see them riding around in covered wagons. The women dressed covered, often in that area, they were Mennonite, they were black, big long dresses and black hair coverings, and the men wore old-fashioned hats. They had homes with no electricity. That's how they live. They choose to live a sheltered existence, deprived of many of the amenities of modern life. No electricity, no cars, no machines, and that's their choice. Young people, though, imagine if you're a young person and you see all this in the outside world, you'd be curious. And so some Amish communities give their children, when they're teenagers, a period called Rumspringa. And that's when they are free. They no longer have to abide by the rules of the community. They leave the community and they go into the modern world and they try all those things that are forbidden to them, or whatever they decide to try. But they have a chance to find out about the outside world. It's kind of cool. And then after that, I think it's a year often, after that year, they make a decision. Do they want to live in the modern world? Or do they want to return to their home community, get married, start their family, and stay put? And if they decide not to return, however, that's it. They can't have their family anymore. So they have to sever those connections. They're not allowed to have both. So it's a big deal. And the idea is that if they have that chance to find out what that world is like, they're going to feel greater commitment to their faith and their community if they return. So it's kind of cool. So now let's imagine that you were curious. You wanted to know, well, do they in fact have greater commitment before and after Rumspringa? And some young people don't return, you know. So the families are taking a chance. So now we're going to use the 5 steps of the hypothesis testing to determine whether they have a higher commitment, whether the hypothesis of the people who give Rumspringa is supported. So population 1. Let's have everyone write it in. What's population 1? I better put the problem back. I forgot to, let me grab this paragraph right here. And I'll put it at the top of our, screen here. Let me get a text box. I have to shrink it. There we go. There. So what's population 1? It's the group that something happened to. Well, young people, right? Young people who what? Well, let's take a look back here and see how we wrote it in our last example. Let me rewrite it here. Schools in which the intervention took place. And then we compared it with schools that had no intervention and therefore no change. The schools in general. So we could say young people who, what did they do? Anyone? Very good. Virgie said young people who took part in Rumspringa. And population 2? It would just be young people who didn't have any change, right? Young people who had no change.
Dr. Russ,
Yes.
so you're just kind of basically generalizing the whole population, because it says 5 young people provided commitment ratings before and after Rumspringa, which we're talking about 5 young people. We're not necessarily talking about young people in general who took part. We're talking about those 5. So should the population 1 be young people who took part in Rumspringa before? And population 2 would be after?
No, that's where you can really get confused. So let's get this.
That's, yeah,
Yeah.
okay,
So
I'm
we're looking
confused.
Yeah, we're looking at young people who took part in Rumspringa, and we're looking at how they changed. So let's put young people who took part in Rumspringa and had their commitment levels measured before and after. Let's add a little more detail. Had their commitment levels measured before and after. We're comparing it to a hypothetical group of young people who didn't take part in Rumspringa, and therefore there was no change before and after. They're, just normal life, but it amounted up to 0, no change. So that does make it a little confusing, but think of what we're comparing. We're comparing mean difference scores, right? And so these people who took part in Rumspringa, they're producing a different score. And we're comparing that to the different scores for young people who didn't take part in Rumspringa and had no change. It can be a little bit to wrap your head around because we're always comparing to like a hypothetical distribution. So this is our difference, mean difference that we're comparing. So it's just one score for these people, and we're comparing it to the mean difference for these people who didn't have Rumspringa. change scores to a population with no change that happened. So that's why it's all right if we just look at our population of these young people who took part in Rumspringa, we know we're just comparing their change with a population that had nothing going on and had no change. All right, no Rumspringa and no change. It's not even and, it's Rumspringa, it's slash. We presume they had no change because there's nothing particular happened to promote a change in one direction or the other. Is that helpful, Sean?
Yes, thank you, Dr. Russ.
Okay, very good. And what are we measuring? What are we counting? Commitment ratings, right? And does this researcher have a hypothesis or a direction? Do we see any words like that in this little description?
Higher commitment.
Okay, so what kind of test is this? One or two tailed?
Would it be one tail high?
It sure would be. Very good. All right, now our research hypothesis, this is where it gets a little weird, but we can state it in terms of our population. We could just write the mean. Let's write it out this way. Mean difference scores for population 1, which is young people who took part in Rumspringa, were no different from population 2, young people with no Rumspringa and no change. So that would be like the statistical way to write it out, and the shorthand would be mu1. What I just made a null hypothesis. You guys, you gotta catch me. I'm gonna put this down here. Look what I wrote. It wrote it's no different. But what I mean to write, mean difference scores for population, the young people who took part in Rumspringa were higher than population 2. And so if I was going to write it out in shorthand, let me put it in pen here instead of in text. I would write mu 1 is greater than mu 2, or I could write mu 1 is greater than 0, because we know the mean for these people with no change is 0. So U2 is going to be 0. So either way would be expressing the same thing.
Dang, man.
What?
Sorry, I was
Oh, that's
looking.
all right. I thought that whole hypothesis was annoying you, Lyle.
I was referring to something else. I thought my mic was off. Sorry.
Oh, that's all right. We needed a little something introduced into this. All right, so this is the way we're writing this. This would be mu1 equals mu2. But we could also put this in words, like if I was going to write this in the conclusion, I would write it different. In fact, I'll wait to the conclusion. So this is like the statistical way of writing the hypothesis. If you felt like writing it, I think this is a good way to write it, just so you're always remembering what we're comparing here. Maybe that's the part we'll have to tease out the most. And so now we can just go ahead and do all that math. So what's the first? Let's see, if you were doing this and you were on your own, what would you do first? How would you approach this? I tend to make a list of what I need usually. so I remember all the things in order. That's how I tend to do it. I know I'm gonna need a lot of columns here though, so I'm not gonna write up there. And let me see if I can get this thing to drag up a little bit. So I'm not cramped for space here. So what we're gonna have is, we know we're gonna need N. We know we're gonna need DF. We know we're gonna need mu, but kind of, not really. We know we're gonna need that mean, and in this case, it's difference scores. You don't always have to write that, it's not the law, but it helps us as we get started. So let's start right here. What is N going to be? Easy peasy, right? Thanks, Virgie, you're the one who's sitting here, so I get to pick on you. DF, what's DF? I'll just call on someone. Celeste? Degrees of freedom? Well, it's easy. I guess a lot of people thought it was so easy. Didn't even need to. All right, anyone? Degrees of freedom?
4.
Thank you.
4.
Right, mu?
0.
Yeah, it's not stated in the problem because you know it's that no change. And MDiff. Now we have to do a little calculating. So the first thing we do to get MDiff is we just go, we have to go X diff equals X2 minus X1. And we know that X2 is after, X1 is before. So we're going to have to do 54 minus 34 equals 20. 77 minus 56 is 22. 73 minus 43 is 30. 50 minus 48 equals 2. And 60 minus 63 equals negative 2. All right. All of this we're done with now. Throw those data aside. Don't need them. We're just going to deal with these difference scores, which are right here. And MDiff is just the sum of all those difference scores divided by N. And in this case, that calculates out to, do any of you have it? If you got 14, you were right. And now we start with all those familiar calculations. We have SS, and we know that FF is the sum of all the deviations. Minus M squared. So let's go ahead and calculate the deviations. 20 minus 14 equals 6. 22 minus 14 equals 8. 30 minus 14 equals 16. 2 minus 14 equals negative 12. And negative 2 minus 14 equals negative 16. Next, we square them. (36, 64, 16 squared is 256. 12 squared is 144. And negative 16 squared is 289. And if we sum all of those up, we get 774. We can continue to calculate E bar, which is SS over DF. And if we run that calculation, we get 193.5. We need VARM equals E bar over N. If we calculate that, we get 38.7. SM is the square root of VARM we calculate it, we get 6.2209. And lastly, T equals, and we can just write MDiff. And we can write minus mu, but we don't really have to because it's always 0 divided by SM. And we get 2.25. Ooh, this one's going to be close again. So let's figure out our last steps here. So mu equals 0, I can just leave that. The T distribution normal. SM we calculated and we got 6.2209. All right, alpha 0.05, DF3. So what's our cutoff point going to be? Let's look it up. This is going to be really close. DF4, did I say, said 3 there from the last problem? Let me change that. DF is 4, n minus 1. And we get 2.13. Which is going to be up here, just past the 2. So I'll write T for alpha equals 2.13. Here's our shaded region. Here's our fail region. Sample T-score, we calculated and we got 2.25. So let's put that in. Excuse me. And our decision, because it's in the reject region, it's way up here. We have to decide to reject HO. And very good. Data from our evidence from our study, data from our study, evidence from our study suggests that young people feel a greater level of commitment to their faith and community after running. Our T is, with a degrees of freedom 4, equals 2.25, and the probability of achieving that result by chance is less than 0.05. So that's it. We're going to end with your questions today. That's what we have. So what questions do we have before we move on?
Questions related to this practice?
Sure, or any questions. They're all kind of related. Anything?
Dr. Russ?
Yes.
So this is this calculations, the only addition to it is the xdiff x2 minus 1, correct?
That's
And
right.
then all the other calculations are the same?
That's exactly right. So this should be a really straightforward assignment for you. You just have 3 practice, you have a quiz. And then 4 application problems. I haven't linked them yet. I'm gonna double check and make sure they're all right, and I'll link them up for you.
Okay, and then the new, in this case, is always 0, correct?
U is always 0. because always think about why, because we're comparing them to a population that didn't have the intervention. And so they would have no reason to have a systematic change before to after. So that's the hypothetical framework, yeah. So that's it. Sean, if you have a minute, I want to chat with you. Virgie, I want to ask you something after the two of you after class, if you don't mind. But other than that, I'm done with what I have for you. If you have questions, I encourage you to get this work done as soon as possible. And next class, we'll just review this a little bit, go through a couple problems, but we're going to move on to chapter 8 in our next class. Once everyone's comfortable with this. All righty. Well, very good. I'll see you next time. And thanks for being here. Come to the classroom. Come to the classroom. What can I do?
Dr. Russ,
Yes,
I'm gonna try to be there on Thursday again.
excellent. That adds so much to our conversation here. Very good.
Yeah, I think I need to be there,
Yeah.
but I'll try to make it on Thursday again.
Okay, very good. We'll do some more problems like this, so you'll be able to review this another time, but I don't think you'll have any difficulties.
I hope not.
All right.
All right, thank you.
All right. Thank you.
Hey, Miss Russ, I'll be there too, next class also.
Oh, beautiful. We'll be so happy to have you here, Colin.
All right. Thank you then.
See you next time. I wanted to, I'll stop the recording. So I asked you this in an email, Reggie, that you might not have seen it, but if you saw it and didn't want to, that's perfectly fine. But I wanted to ask the two of you, I feel a little, I don't want to put you in any way on the spot, and it's not a big deal, yes or no, doesn't matter. But in my old university, there's an event called Global Table, because we always had a lot of international students and we wanted them to have a chance to talk about where they're from, where their cultures. And they wanted me to see if any students from here would be willing to zoom in and talk about living here. And they actually asked me if I wanted to do it. And I said, well, I feel disingenuous, like speaking as if I know, because I'm an outsider. And so then we talked it over and said, well, maybe some students or some people you know would want to come. And so I just thought of the two of you because I know, Sean, I thought of you because every time you speak in class, you just seem to manifest the value system. It just seems to exude from you. And I thought you might have things to share. And Virgie, I thought of you because you have such a leadership role and activity level, and because you're a mother and all of those things. And it's a really short event. It's just at lunchtime. It's November 4th at noon. And I wanted to know if either of you would have time or be interested or willing to just jump on there and chat a little bit about whatever, it'll probably be questions. I mean, probably we'll start out with me sharing a little bit about, I mean, I don't think there'll be students there who still know me, but so I'll share a little bit about who I was there and then why I came here. And then it might be more Q&A and it's just a lunchtime talk. I know the psych students will be there. And so I wanted to ask you, and I don't want you to answer now because I want you to feel absolutely free to take your time to think about it. And I also wanted you to know that, like, if you decline for any reason, you don't even have to tell me why, and it wouldn't impact my thoughts or feelings about you, and it certainly wouldn't impact anything else. So I just wanted to ask you if you'd consider that, and for you to take your time to think about it, and maybe let me know, because they want to make some flyers. And they want to know, usually we put the pictures of the presenters on the flyers and they're posted up around campus up there. So, and the one thing is, if you're looking at putting something on your resume, this is a good kind of thing to put on your resume. But you both probably have plenty for that. So you would really be just doing it because you have rich experience to share. So I just wanted to put that out there and see if you'd consider it, and that's all. And thank you for coming to class and participating today.
Dr. Russ,
Yes.
November 4th, did you say, from noontime?
Yes.
Okay, and this global table will be with students here or at another university?
Students at Dickinson State University in
Oh,
North
okay.
Dakota, where I taught before I came here.
Oh, okay.
Yeah, and faculty, students and faculty is the people who would be there.
Mhm. Would it be similar to like how you had that one previous student you had and he presented to us on but his was more like his profession as a I believe uh, he established a program up there in North Dakota and he presented to us. Would it be similar like that, but vice versa on culture?
Oh, it would be a reverse of that, yes.
Mhm.
It would be, yeah, like he talked about his work and this would be a reverse, like probably we chat ahead of time about what you might feel you would talk about. You might just be describing what your life growing up here is like, you know, that might be.
Oh, okay.
Or like what you're, maybe that's not what you'd want to talk about and you decide that you wanted to talk about. Maybe Virgie wants to talk about like what it would be, if you did it, would talk about like what it is to represent Navajo people in the public forum, maybe in public sharing.
Oh, okay.
And the psychology students will be there, I'm told. So they might want to know a little bit about, well, what is Navajo psychology?
Hmm.
I invited Pernell Perry, I'm just listening to another class too, about that. I don't know if he can make it either. So I'm
Yeah.
putting the feelers out there.
Okay. When do we have to let you know?
You know, if you were able to know by Thursday's class, I think that would help them to get the flyers out. He messaged me yesterday and I knew I needed to deal with this. So I need to probably get back to him by Thursday if I could.
Okay. All right. Let me.
Doing it, and no worries either way. Honestly, thank you so much and have a good afternoon.
Okay. All right. Yeah. Thank you for keeping us in mind for something of this. I guess this level of experience to be able to share some of our insights about growing up. Sort of like res life, I guess.
Well, and all that beauty, there's a lot of beauty up here.
Yeah.
So that's what I thought it might be nice for them to experience.
Okay. All right. I will talk to my bosses here and see what they say. And if I get,
And they can
go
come
ahead.
if they want to. Your family could talk if your wife and or children. Anyhow, thank you so much. And I'll
Okay.
see you next time.
All right. Thank you so much, Dr. Russ. Have a good day.